Hello everyone, welcome again to our generative AI from scratch series. So today in this video, we'll be moving ahead towards deep learning essentials. So what is deep learning? So we will consider the same example that we were using in our past videos. So like that small kid who wants to play outside. So basically first they learn with a simple rule like if it is sunny, then play outside, like perceptron, the simple network. Okay. Uh, but later the kid learns the complex rules as well. For example, if it's sunny, but the ground is slippery, don't play. If if it is cloudy, you finished homework early, so it is okay to go out and play. So these are some complex rules that getting add on. So basically, now kid will be able to understand more output. Either he wants to play or he should play. Either he should play or not, based on the multiple inputs. So that is deep learning, learning complex patterns from lots of data, not only a single input, but from the many inputs or many data, we learn different patterns. Okay, so there is no single rule. There will be many rules in the form of different layers. Okay, instead of two inputs, there will be thousands and millions of inputs. Instead of simple addition, there will be non-linear transformation like curves and threshold, and then it will calculate the output. So if we compare deep learning and machine learning, so there is a major difference between both of these. So if we consider the data size, so in machine learning, the data size is very small and you can say or medium. But in deep learning, we cannot predict the data size. It can be very huge, okay, for a normal human being to even understand. Okay, so that where the deep learning is very essential to consume lot of data and then provide the significant output or answers out of it. And if we talk about features, so in machine learning, we manually choose features, but in deep learning, it is automatically learning. It is learning from its mistake and then it is enhancing itself. And if we talk about model complexity, so the machine learning one is quite simple with some rules defined, but the deep learning one has the complex multi-layer network. And the problem type we provide in machine learning, it's kind of a tabular or structured data where we majorly work on the data kind of thing for a company where we know our data. But when it comes to deep learning, it will be any kind of data, either to images, videos, text, charts, anything. It could be anything. So the data is not fixed in the deep learning. So why we need multiple layers when we can work on single layer? So now we'll understand how these multiple layers help each other to process a large amount of data. So for example, layer one has the basic patterns, and then layer two will have the combination of some basic pattern, and then layer three will have some complex pattern like object and ideas, and then final layer would have some decision. So if we take an example, when we want a model to recognize a cat, if we provide it an image, then how it will recognize that it's a cat. So it will have multiple layers. So for example, if we talk about only three layer here, so first layer will uh, find the edges and corner in the picture. Okay, it will see how these edges and corners are connected. Then second layer will join the edges to actual shape like ears and eyes. And then third layer will identify actual which kind of pattern it is following and what animal it is, or either it's an animal or human. So then it will provide us the output that this is a cat. So as now we understand, we will be needing the multiple layer architecture, multiple layer model. So then comes the neural network, and now we'll understand the neural network architecture. So now in this example, I'm creating some neurons. So basically the first one is N1, then I have N2, then N3, N4, and N5. Okay, so the first one pair is for input. This is the input layer. Okay, so this the second one is the hidden layer, and the last one is the output layer. Okay, so inside input layer we have two neurons. For hidden we have two neurons, and then for output we one neuron. So input will be used like providing the input, and these are the edges that are connecting it, or we can say weight. So the input that we have taken here, like two input, for example, we have taken in the previous videos as well. That one for homework and one for weather. Okay, and then we have hidden layer. Hidden layer is just for basically for doing the calculation, where we add the bias and all, and then we do some calculation. And the final layer is the output layer, where we provide the actual output to the user. So this is the actual diagram where it is showing us the simple network. So as I told you, two input neurons, we have features like weather and homework, and then one hidden layer we have also with two neurons with intermediate calculation, where the actual calculation will be performed, and the final will be the output neuron. There could be multiple hidden layers as well, where we will be doing the multiple kind of calculation. Okay, we can have the multiple input layer as well. Okay, and then we have one single output layer. So I'll explain you this with an example in few minutes, how these calculations are done. So why activation functions are needed? So without activation function, the multiple layer would be a single big equation. Okay, so to simplify it and to make it bit simpler for the calculation, we have the activation function that we can use, and we can simplify our calculation, and then we can calculate the output. So some example of activation function we have, like sigmoid, that I've also shown you. So it has one function that we use for our calculation. It is good for when we are doing the binary clarification, like we want to get value between 0 to 1. And then we have rectified linear unit, which is good for hidden layer. Okay, it makes negative number 0, and it makes the learning faster for a model. And we'll be using one of these function, like majorly the sigmoid, in our upcoming example. Now, what is forward propagation? Forward propagation is the process where data flows from input layer to hidden layer, and then hidden layer to output layer. This is forward propagation. We also have backward propagation that we will be learning in our next video. But in this video, we'll be solving an equation using the forward propagation and getting the output from a model. The steps involved in the forward propagation calculation are: first, we multiplies each input by its weight. Then we add some bias to it, and then we apply an activation function like sigmoid or ReLU. And then we passes the final result to the next layer. And then next layer again perform this operation. So this process continues to follow in a loop until the loss gets decreased to a very lowest value. Okay, so basically we get the most accurate answer out of it, and until then these loop will continue to perform within the layer. So the goal is to make a final decision, and the final decision should be very accurate or very close to the accurate. So now let me show you. We'll be taking that same example, weather 1, and which is for basically the sunny day, and then homework is equals to 0, which is homework is not done. So the input format would be x is equals to 1 comma 0. So this is our input array. Now we will take the weight and bias array. Okay, so let's take a weight of 0.5 minus 0.6. This is one array, then one more 0.8, and then 0.9. Now let's take the bias array. We'll be having 0.1 and then 0 minus 0.2. Then we will be taking weight 2, 1.2 minus 1.1, and then bias 2, that will be 0.05. So the weight one is weight from input to the hidden layer. Okay, this will be a weight from input layer to hidden layer, and the bias one will be the bias for hidden neuron. Okay, for hidden neurons, we have taken this bias, and then W2 is the weight from hidden layer to the output layer. And the last one, bias 2, is output for output neuron. Okay, now let's calculate by applying those steps. So for neuron 1, we will calculate it. So for neuron 1, we will first multiply input with weight. Value is 1 into 0.5, and then we'll add another input, that is 0 into 0.8, and then we'll add the bias 0.1. Now let's calculate it. This will be 0.5, and then this will be 0. Oh, sorry, 0, and then 0.1 is equals to 0.6. So now we'll calculate for neuron 2, and that will be Z12, and that will be 1 into 0.6 of our value, faster than 0 into 0.9 for another input, and then addition of 5, that is 0.2 minus, and then calculate it. Oh, sorry, this should be minus 0.6. Yeah. So this will be 0.6 in minus, then plus 0, then my, yeah, minus 0. Okay, then this is going to be 0.8 in minus. Okay, so for N1 and N2, we have calculated the value 0.6 and 0.8 minus. Now let's apply the sigmoid function. So for N1, we'll be adding sigmoid function as A11 is equals to sigmoid of our first output, that is 0.6, and then 1 by 1 plus to the power minus, and our value 0.6, which will be around 0.645. And then for N2, we'll again apply the same formula, A12, and that will be sigmoid of minus 0.8. And then this will be 1 by 1 plus e to the power 0.8. And that will be close to 0.310. Now, this is done for input layer. Now, let's do the same calculation for the output. And the output for the hidden layer is 0.645 and 0.310. Okay, so this is the output for our hidden layer. Now, we'll be doing the calculation for our output layer. So it will be set to equals to 0.645 into 1.2, then for another 0.310 multiply by minus 1.1 and then addition of weight, that is 0.05. That is for our output weight here. And then Z2 will become 0.774 and minus value with 0.341 plus 0.05. So the final value will be 0.483. Now let's apply the sigmoid function to this value. So the output will be sigmoid of 0.483, and that is 1 by 1 plus e to the power minus 0.43, which is close to 0.618. So this is the final value which we are getting as the output. So the final output inputs, whether 1 and homework 0, came as 0.618. And if we take it in the percentage, so it will become 61.8%, which is moving more towards 1. So that means that child can play. Okay, I hope you get it now. Now we'll see with running it on our Google Colab. So yeah, we are inside our Google Colab. So same, we have defined one sigmoid function because we'll be applying this uh, functions, and then we have taken this input. Okay, so you must be aware about these input now, and we have taken the weight input, which is the W1. Okay, which is for our input layer. From input to hidden layer, these are the weight which contains 2 neurons. Okay, and then we have weight from hidden to output layer. Then this is weight 2. Okay, we have bias 1. Okay, B1 for the hidden layer, and this is the array we have taken, and the bias 2 we have taken 0.05. Now we will do the forward propagation. Okay, so the simple logic we are also adding here. We are multiplying the input with the weight, and then we are adding the bias to it. And then after that, we are applying the sigmoid function. Okay, and then same we are doing for the next layer, that is output layer. And we are using the values same here, input multiply with weight and then adding the bias. And then once we have the final output with us, uh, then we are basically printing that output. And the output is coming as 0.618. Let me re-execute it and show it to you. Yeah. So for the hidden layer output, we get 0.645 and 0.310. And the final output we get is 0.618, which is 61.8% that child can play. So I hope now you understand the forward propagation, how we do the calculation in forward propagation. In the next video, I'll let you know about the backward propagation and the calculation. So now see you in the next video. Thank you.